Right now, inside an unmarked data center in Northern Virginia, a single artificial intelligence query is consuming enough electricity to boil a gallon of water. Not because the AI is incredibly smart, but because the software running it is shockingly wasteful. We have spent billions hoarding the world's most advanced microchips, only to run them on generic code that leaves their most powerful components completely idle. For the last 5 years, the recipe for building artificial intelligence was simple: buy more GPUs, burn more power, and scale. But in 2026, that brute force era has officially collided with physical reality. Data centers are threatening local municipal grids, cooling water is scarce, and the returns on training ever larger models are flattening out. An academic paper from Cornell University titled "An Alternative Trajectory for Generative AI" warns that we have entered a permanent systemic crisis. The economic burden of AI has shifted from a one-time training cost to a recurring, unsustainable tax every time a model runs. The physical limits of our world have forced a choice: either make software radically more efficient or watch the AI revolution grind to a halt. To understand why the industry is hitting this wall, we have to look at how modern AI models actually think. The transition to advanced reasoning models has fundamentally changed the math of computation. In the past, running an AI model was a simple transaction. You asked a question, the model processed it once, and spit out an answer. But today's reasoning models do not just respond. They engage in internal chain of thought processing. They generate, evaluate, and discard thousands of internal tokens before they ever show you a single word. This means a query that used to take a fraction of a second now keeps a cluster of GPUs burning for minutes at a time. This internal thinking process has inflated the compute cost per query by multiple orders of magnitude. The old strategy of throwing more hardware at the problem is financially ruinous. If every search query of the future requires 5,000 internal tokens of deep thinking, we simply do not have the silicon or the power grids to support it. The crisis is no longer about how we train these systems. It is about how we keep them running. To solve this crisis, we have to look past the neural networks themselves and focus on a deeply unglamorous layer of the technology stack: the compiler. Most people assume that when you write a line of PyTorch code, the GPU reads it directly and performs the math. But microchips do not speak Python. A compiler is the unseen translator that sits between abstract, high-level mathematical software and the raw, physical silicon registers of a chip. It is the compiler's job to translate elegant equations into messy, physical instructions that route electrical currents through billions of transistors. To understand why this is so difficult, imagine a state-of-the-art robotic assembly line. The robot arms can move at near speed of light velocities, capable of assembling a machine in microseconds. But there is a catch. The parts they need are stored in a massive warehouse miles away, and they have to be delivered by slow-moving cargo trucks over a congested, narrow two-lane highway. If the trucks are not perfectly scheduled, the multi-million-dollar robots spend 90% of their time sitting completely still, waiting for a shipment of screws. This delay is the reality of modern GPU computing. It is known as the memory wall. A modern NVIDIA graphics processor contains two main types of memory. There is high bandwidth memory, or HBM, which is massive but sits relatively far away from the processors. And there is SRAM, which is incredibly fast but extremely small, located directly inside the processing cores. Every time a GPU performs a mathematical step, it must fetch data from the slow HBM, pull it into the fast SRAM, execute the operation, and write the result all the way back to HBM. When you use generic compilers, they translate each mathematical step individually. This creates a disaster known as a memory bubble. The processing cores execute their math in a nanosecond, and then sit idle, starved of data, waiting for the next instruction to travel across the slow memory bus. In standard AI workloads, these silent memory bubbles eat up more than 70% of a chip's theoretical performance. You paid for a state-of-the-art supercomputer, but because of poor compilation, you are running it at the speed of a decade-old machine. This is where the competitive landscape of artificial intelligence fractured. While the largest technology giants in Silicon Valley were busy writing massive checks to buy hundreds of thousands of NVIDIA chips, engineers at smaller, resource-constrained firms realized they had to take a different path. They looked at the massive inefficiencies in the software stack and decided to bypass generic frameworks altogether. Instead of relying on automated compilers to translate their models, they began writing custom Triton kernels and bare metal parallel thread execution code, or PTX. This is assembly-level software. It is incredibly difficult to write, requiring engineers to manually dictate exactly which registers inside the physical silicon store which pieces of data at any microsecond. By writing code that communicates directly with the raw silicon, they eliminated the layers of corporate software bloat. They did not win by having the most hardware. They won by ensuring that every single transistor on the chips they did have was firing at maximum capacity every microsecond of every day. To see how powerful this approach is, we have to look at a technique called kernel fusion. In a standard software stack, if you want to perform 3 mathematical operations in a row, the compiler executes the first operation, sends the result back to the slow high-bandwidth memory, pulls it back to the core for the second operation, and repeats the process. A custom-engineered fused kernel changes this completely. It stitches those 3 distinct mathematical operations into a single continuous instruction block. The data is pulled from the slow main memory exactly once. It enters the hyper-fast SRAM inside the processing core, undergoes all 3 transformations in a single pass, and is written back only when the entire sequence is complete. This single optimization reduces memory traffic by up to 80%. It turns a congested highway of slow cargo trucks into an elite conveyor belt system. By designing custom compilers that automate this fusion process, engineers are achieving performance gains that would normally require buying twice as many physical GPUs. The implications of this shift stretch far beyond corporate balance sheets. They are transforming global geopolitics. For years, the United States has relied on strict export controls to restrict competitor nations from acquiring the latest generation of high-end silicon. The assumption was simple. If a country cannot buy the newest chips, they cannot compete in the AI race. But this hardware-centric view ignored the power of low-level software engineering. If an engineer can write a custom compiler stack that doubles the efficiency of an older generation chip, they effectively neutralize the advantage of their competitors' newer hardware. By open-sourcing these hyper-optimized kernels, teams worldwide have democratized this efficiency. An organization running thousands of older processors with custom compiler designs can now deliver inference speeds that match or exceed competitors running state-of-the-art silicon on standard software. The hardware monopoly has been cracked, not by building a rival chip foundry, but by writing smarter code. We are moving toward a future where the scale of an AI system is no longer measured solely in parameters, data centers, or megawatts. As the academic community warned, the current path of brute force scaling is hitting its physical and economic limits. The next stage of the compute race will not be won by the company that buys the most silicon or consumes the most grid power. It will be won by the unseen architects, the compiler engineers, the kernel designers, and the low-level programmers who refuse to let a single watt of energy go to waste. By building software that respects the physical constraints of silicon, they are proving that true innovation does not require a bigger footprint. It requires a deeper understanding of the machine.